Hello everyone, my name is Gang Fu. I am a PhD candidate from Wuhan University, China. The paper I will be presenting today is titled Structure Preserving Image Smoothing with Semantic Cues. Here is a teaser image. From this figure, we can clearly see that our method can effectively remove textures while preserving moving structures. In comparison, some textures are wrongly residue in the results produced by other compared state-of-the-art methods. Existing deep learning-based edge detection methods can powerfully extract the meaningful edges of objects with different sizes from textures, which provides us with useful semantic cues for structure preserving image smoothing. We observe that the original L0 image smoothing method proposed by Xu fails to remove large-scale textures without inducing blurring small-scale structures. In contrast, inspired by learning-based edge detectors, we try to combine semantic cues to the original L0 gradient minimization framework to obtain high-quality results without inducing the issue mentioned. A direct idea is to construct a weight L0 gradient minimization, as shown in the equation. Here, E is the edge confidence map estimated by an existing deep learning-based edge detection method. We also observe that our purpose-weighted L0 gradient minimization framework can be further improved due to the possible inaccuracy of edge detection, which often leads to some weak textures residue in structures. We thus utilize a recursive scheme to further remove high contrast textures. We further utilize median filtering operation to further suppress small textures around structures. As shown in this figure, we can clearly see that without the median filtering, many textures are residue in the output structure image. As median filtering size increases, small textures around edges or structures are effectively suppressed. For model solver, a direct solution is based on the orange L0 gradient minimization scheme. However, we also proposed a data parallel IRLS core on GPU, enabling the faster speed and real-time performance. Some previous workers have explored the feasibility of data parallel PCG for the faster solution of the problem similar to ours. For the faster implementation on GPU, we also adopt a similar GPU-based PCG scheme to make use of the sparsity pattern of the system matrix. In the PCG iterations, we compute the entries of the system matrix on the fly and never store explicitly. We also utilize inverse diagonal preconditioning scheme. Moreover, we further manipulate the regular grid structure of the image domain to separate our optimization into many local sub-problems. Based on the data parallel PCG server, these sub-problems can be fast and effectively solved in the shared GPU memory. In the following, we will show our experiments. Here, we provide some visual comparison with state-of-the-art methods. From this figure, it shows that the RTV method can remove non-uniform and multiple-scale textures. The drawback of this method is that it can blur small-scale structures while removing large-scale textures. for example, White House, 4th row in this figure. The semantic filtering 14.8 can effectively extract the subjective, meaningful structures and avoid the drawback of RTV. But we found that this method sometimes results in boundary fuzziness issues. For example, color strip clothes, 4th row in this figure. In contrast, our method can effectively remove high contrast textures while preserving subjectively meaningful structures, while benefits from the combination of edge detection technique and L0 gradient minimization framework. In our work, the quantitative comparison is also made. We basically treat the magnitude of improvement of the edge detector caused by the pre-processing as a reference for image smoothing quality. We select two error metrics including mean absolute error MAE and weighted F-measure error WFME. As can be seen in this table, our method achieved the lowest MAE and WFMAE values. Here is the time consumption comparison result. It shows that our server of CPU version has achieved comparable and even faster speed, while our server of GPU version has achieved lowest time consumption. Our method can be used to multi-scale detail manipulation without inducing artifacts along the high contrast edges. A visual example is shown here. Visually speaking, our method can produce nature-looking results without inducing artifacts. Here is an example conversion result for the DIPS upsampling application. For the input DIPS map is severely noisy and of low resolution. Our method can be applied to solve this issue. As can be seen in this figure, our upsampled DIPS map rarely suffers from the text copy problem, while preserving the edges or contours well. There are many noises residue in the DIPS map refined by bilinear interpolation method. For Liu 24, their result is often with streaks-like artifacts. For John 48, their result often suffers from the text copy artifact, for example, painting on the wall and making some Reaper-like artifacts. Here is an example conversion result for the application of intrinsic image decomposition. Our weighted smoothing prior can be used as a reflectance sparsity prior in some existing intrinsic image decomposition framework. Compared with previous sparsity constraint, our method can avoid some visual artifact often caused by clustering-based method, resulting in promising result. Here is an example conversion result for application of low-light image enhancement. As can be seen, the method 14 often overexposes the bright regions, for example, the golden color headdress and the face of statue. And sometimes the method of 15.3 slightly overexposes some small regions. For example, extending the finger and the face of statue. In contrast, our method can produce better results with clear details and natural colors. We provide more analysis for our proposed method. In this figure, we show the relationship of our method to the original L0 image smoothing. In this experiment, we interactively conduct original L0 image smoothing in the same way, as our model, and can observe that there is no significant improvement in their result. In contrast, our results have been effectively improved. We conduct an experiment for our method use different normal regularizers. From this figure, in conversion to L1 norm, our method with L0 norm can more effectively remove textures while preserving meaningful structures. In this figure, we plot average PSNR, peak signal-to-noise ratio, value between two adjacent interactions as the function of the number of interactions. We can see that the PSNR value is greater than 14 dB just after 2 or 3 interactions, which means that some very subtle changes are not visually observed. Of course, our method has a limitation. Our method depends on external edge detectors, and any error presented in edge detection is propagated into our structural extraction. Even existing state-of-the-art edge detectors cannot entirely and full accurately detect the edges of objects, especially in complex scenes and objects with a lot of noises. A visual example is shown here. In this work, we present a novel image smoothing method combining L0 image smoothing and a state-of-the-art learning-based edge detector. We developed a novel approximate solver for original L0 gradient minimization problem, which can achieve real-time performance. We demonstrated the applicability of our method on many examples, including detail enhancement, depth of sampling, intrinsic image decomposition, and low-light image enhancement. In the future, we will extend our method to handle videos and make more beneficial applications. That's all. Thank you.